In today's video, we will tackle about the numerical series tests. Number series questions in numerical reasoning assessments consist of a group of numbers that share a logical rule based on elementary arithmetic. Numbers in a series are described as terms, and they are presented in a sequence with gaps. The candidate must find the missing terms to complete the questions. Generally, there are three types of questions asked from the number series. 1. A numerical series is given in which a number is wrongly placed. You are asked to identify that particular wrong number. 2. A numerical series is given in which a specific number is missing. You are required to find out that missing number. 3. A complete numerical series is followed by an incomplete numerical series. You need to solve that incomplete numerical series in the same pattern in which the complete numerical series is given. Here are the different types of number series that we must know. These are the common patterns followed by number series. Perfect square series. It is a series based on perfect squares of a number in a specific order. Example, we have 324, 361, 400, and 441. What's the next number of the sequence? To find the next number, you need to find its square root. The square root of the first number, 324, is 18, which 18 to the power of 2 is 324. The square root of the second number, 361, is 19, which 19 to the power of 2 is 361. The square root of the third number, 400, is 20, which 20 to the power of 2 is 400. Lastly, the square root of the fourth number, 441, is 21, which 21 to the power of 2 is 441. So, to get the next number, we need to find a number that its square root is 22, where 22 to the power of 2 is 484. The next number of the sequence will be 484.
So in the given example, there are the series of perfect squares that starts in 144, followed by 169, 196, 225, and the missing following perfect square number. So before we solve and find the missing following number, let us first understand how to solve the first given number, which is the 144. So now we have the chart. So we will find the equal integers that shows the 144 as the answer. So first, let's find the 144 number. So here's the 144. We can find the 144 number in the equal integers, which is the 12th upper timetable, and the lower upper timetable, which is also 12. So that is called the equal integers, and we will find the 144 number. So here is the solution. 144 is equal to 12 square. Next is the 169. So 169 was placed in between the equal integers 13 upper times table and 13 lower times table. So 169 is equal to 13 square. And then next is the 196. So 196 was placed between 14th upper times table and 14th lower times table. So 196 is equal to 14th square. And then next is 225. So 225 was placed here and between 15th upper times table and 15th lower times table. So 225 is equal to 15 square. So now we only have to find the missing following numbers after the 225 perfect square. It is clear that the 16th upper times table and 16th lower times table is the equal integers of the missing perfect square number. So what is the missing perfect square number? So here it is the 256. To complete the answer in this example, we have 144, 169, 196, 225, and the missing perfect square number is 256.
Perfect cube series. It is based on the cubes of numbers in a particular order. Example, let's say we have 512, 729, and 1000. What's the next number of the sequence? To find the next number, you need to find the cube root of each number. Now, 512 is the same as 8 to the third power, or 8 times 8 times 8 is 512. 729 is 9 to the third power, or 9 times 9 times 9 is 729. 1000 is 10 to the third power, or 10 times 10 times 10 is 1000. Therefore, the next number in the sequence has to be 11 to the third power, or 11 times 11 times 11 is 1331.
For example, find the next number in the series: 8,000, 27,000, 64,000, and unknown. So let's find the next number in the series. Now to solve the problem, let us first start with the first term, which is the 8,000. The first thing we do is focus on the first digit of the number. The first digit of each term has a cube number of some number. So let's start with 8,000. So let's look at the first digit. So 8. The 8 here is a cube number of 2 to the power of 3. So therefore, the perfect cube number of 8,000 is 20 to the power of 3. So to solve this, let's multiply the number by itself 3 times. So 20 times 20 times 20. So 20 times 20 times 20 is equals to 8,000. So therefore, 20 to the power of 3 is a perfect cube number of 8,000. Now let's go to the next number, 27,000. So let's look at the digit 27. So 27 here is a cube number of 3 to the power of 3. So therefore, the perfect cube number of 27,000 is 30 to the power of 3. So let's solve 30 to the power of 3 if it is 27,000. So 30 times 30 times 30. So 30 times 30 is 900. The 900 times 30 is 27,000. Now let's go to the next number, 64,000. If you will notice, 20 here is the first number, then 30 here is the next number. So therefore, 20 is added by 10 to the next number. So 20 plus 10 is equals to 30. Now, for the next number, let's add 30 to 10. So the next number is 40 to the power of 3. Now let's solve 40 to the power of 3 if the answer is 64,000. So let's solve 40 to the power of 3. So 40 times 40 times 40 is equals to, so 40 here times 40 is equals to 1,600 times 40 is 64,000. So therefore, 40 to the power of 3 is equal to 64,000. Now for the missing number or the next number, in this part, we add 10. So therefore, we add also 10 for the next number. So 40 plus 10 is equals to 50 to the power of 3. Now let's solve here to find the next number in the series. So 50 times 50 times 50. So 50 times 50 here is 2,500 times 50 is equals to 125,000. So therefore, the next number in the series is 125,000. So that's it.
Geometric series. It is based on either descending order of numbers, and each successive number is obtained by dividing or multiplying the previous number by a specific number. Here is an example. We have 4, 36, 324, and 2,916. What's the next number of the sequence? If we take the second term number 36 divided by first term number 4 is 9. And the third number 324 divided by the second term is 9. So we have a common ratio. If we multiply 4 by 9, it will give us 36. And if we multiply 36 by 9, it will give us 324. Lastly, if we multiply 324 by 9, it will give us 2,916. So, to find the next number, we gotta multiply 2,916 by 9, and that's gonna give us 26,244.
For geometric series, identify the next geometric series. 3, 15, 75, 375, 1,875, and the missing number. We write here the given. 3, 15, 75, 375, 1,875, and the missing number. As you can see, the given number, it is sorted from lowest to highest number. We can say that this is an ascending order of numbers. But first, we use division to divide the second and first given numbers. 15 divided by 3 equals to 5. So we can get the specific number, which is 5, to multiplied by the existing given numbers. We go first for number 3. 3 times 5 equals to 15. As you can see, the answer is the next given number. Here. Next. 15 times 5 equals to 75. Then 75 times 5 equals to 375. Then 375 times 5 is equals to the last given number, which is 1,875. Find the 1,875 times 5 is equals to 9,375. See, so we put here 9,375.
Arithmetic series. It consists of a series in which the next term is obtained by adding, subtracting a constant number to its previous term. Let's say we have the numbers 4, 9, 14, 19, 24, 29. What is the next number of the sequence? Now, what we need to do is to find a pattern. Notice that each number has a common difference of 5. To go from 4 to 9, you need to add 5. Likewise, to go from 9 to 14, you need to add 5. And 14 to 19, you need to add 5. 19 plus 5 is 24. And 24 plus 5 is 29. 29 plus 5 is 34, and so forth. In which, to find the next number of the sequence, we just need to add 5 on every last number.
Here's a series. 3, 11, 19, 27. What will be the next number? First, we will find its common difference by subtracting the second term to the first term. 11 minus 3 equals 8. 8 is its common difference. To check, we will add the terms to the common difference. First is 3 plus 8 equals 11. 11 plus 8 equals 19. 19 plus 8 equals 27. And 27 plus 8 equals 35. So 35 is the next number to the series.
Two-stage type series. In a two-step arithmetic series, the differences of consecutive numbers themselves form an arithmetic series. Let's say we have the sequence 1, 3, 6, 10, and 15. Find the next terms of the sequence. So what is the common difference? If we take the second number 3 and subtract it by the first number 1, we will get 2. If we take the third number 6 and subtract it by the second number 3, it will give us 3. If we take the fourth number 10 and subtract it by the third number 6, it will give us 4. Lastly, we take the fifth number 15 and subtract it by the fourth number 10, it will give us 5. Now, we get an arithmetic sequence 2, 3, 4, and 5. Hence, 6 will be added to the last number given, so the answer would be 15 plus 6 is equals to 21.
4, 8, 16, 28, 34. What will be the next number? In this series, we will subtract each term to know its arithmetic pattern. So 8 minus 4 equals 4. 16 minus 8 equals 8. 28 minus 16 equals 12. 34 minus 28 equals 16. So you have an arithmetic pattern of 4, 8, 12, 16, which is a common difference of 4. So we will add 4 to 16 to have 20, which will be added to 34 to know the next number. 34 plus 20 equals 54. And it is the next number in the series.
Mixed series. This particular type of series may have more than one pattern arranged in a single series, or it may have been created according to any of the unorthodox rules. Example, let's say we have 10, 22, 46, 94, and 190. What's the next number of the sequence? Here is the solution. You must multiply it by 2 and add it by 2 to know the next number in the series. So you will notice that it has more than one pattern arranged in the series. We have the first number 10 multiplied by 2, which is 20. Added by 2 is 22. The second number 22 multiplied by 2, which is 44, added by 2 is 46. The third number 46 multiplied by 2 is 92. Added by 2 is 94. The fourth number 94 multiplied by 2 is 188. Added by 2 is 190. Lastly, the fifth number 190 multiplied by 2 is 380. Added by 2 is 382. So the missing number is 382.
To try this, identify what is the next number series of 2, 10, 34, 106, and 322. So 2, 10, 34, 106, 322, and the missing series number. So in this number of series, we need to multiply the first number to 3 and add by 4. So 2 times 3 plus 4 times 3 plus 4 times 3 plus 4 times 3 plus 4 times 3 plus 4. So that is our pattern. So let's list it down. 2 times 3 is equals to 6 plus 4 is equals to 10. So as you can see, the answer is the next number series. So 10 times 3 is equals to 30 plus 4 is equals to 34. So same the number of series, so 34 times 3, so equals to 102. 102 plus 4 is equals to 106. So 106 times 3 is equals to 318 plus 4 is equals to 322. Find the 322 times 3 is equals to 966 plus 4 is equals to 970. So our next missing series number is 970.
Arithmetical-geometric series. As the name suggests, arithmetical-geometric series is formed by a peculiar combination of arithmetic and geometric series. An important property of arithmetical-geometric series is that the differences of consecutive terms are in geometric sequence. Example, let's say we have 1, 4, 8, 11, 22, and 25. What's the next number of the sequence? In the arithmetic series, notice that the common difference is 3, while the geometric, we have the common ratio of 2, where the first number 1 added by 3 is equals to 4. The second number 4 multiplied by 2 is 8. The third number 8 added by 3 is equals to 11. The fourth number 11 multiplied by 2 is 22. The fifth number 22 will be added by 3 is 25. Lastly, the sixth number 25 will be multiplied by 2, where we can get the next number of the sequence, which is 50.
Arithmetical-geometric series. For example, insert 3 numbers between 4 and 64 so that the resulting sequence forms a GP. Let's try to solve this example. So here's the solution. Let G1, G2, G3 be the 3 numbers to be inserted between 4 and 64. And now, this is the formula we'll be using for this equation. R is equal to parentheses B over A close parentheses 1 over N plus 1. A is equal to 4, B is 64, and our N is 3. Since 64 is our B, then let's put 64 over A. A is 4, then 1 plus, and our N is 3, so let's put 3 plus 1. Let's solve. 64 over 4 is 16. And then 1. 3 plus 1 is equal to 4. And solve, the final is 2. The answer 2 will serve as multiplicand in order to solve for G1, G2, and G3. And now let's start to solve. First, let's solve for G1. So, G1 is equals to 4 times 2. Remember our 2. This will serve as our multiplicand in order to get the product, the answer for G1. So 4 times 2 is equals to 8. And now, let's start to solve for our G2. Remember the product from G1? It will serve as our multiplier to solve the answer for G2. So 8 times 2 is equals to 16. And now for G3. So 16 times 2 is equal to 32. The product of G2 will serve as our multiplier in order to get the product for G3. So 16 times 2 is equal to 32. And now let's try to check if these are the correct answers that will complete the sequence. So 32 times 2 is equals to 64. Now 4, 8, 16, 32, 64.
Geometrical-arithmetic series is the reverse of arithmetical-geometric series. The differences of suggestive terms are in arithmetic series. Example, we have 1, 2, 6, 36, 44, and 440. What's the next number of the sequence? Here, the first number 1 will be multiplied by 2, which 2 is the second number to get the next number. 2 will be added by 4 to get the third number, which is 6. And 6 will be multiplied by 6 to get the fourth number, 36, where 36 added by 8 is 44, which is the fifth number. And 44 multiplied by 10 is 440, which is the sixth number. So, to get the missing number in the sequence, we will add the sixth number 440 by 12 to get 452. Twin alternate series. As the name of the series specifies, this type of series may consist of two series combined into a single series. The alternating terms of this series may form an independent series in itself. Example, we have 3, 4, 8, 10, 13, and 16. What's the next two numbers in the sequence? As we can see, there are two series formed. Series 1, 3, 8, and 13, with a common difference of 5. The first term number, 3 added by 5, is 8. The second term number, 8 added by 5, is 13. The third number, 13 added by 5, is 18. Series 2, 4, 10, and 16, with a common difference of 6. The first number 4 will be added by 6 is 10. The second number 10 added by 6 is 16. The third number 16 added by 6 is 22. So, the next two terms of the series should be 18 and 22 respectively.
So what is the next two missing terms of the series? In 2, 4, 11, 15, 20, 26, 29, and 37. 2, 4, 11, 15, 20, 26, 29, and 37. Here, okay. Since this is twin alternate series, it has two series combined into a single series. So we need to break it into two groups. So the first group is 2, 11. So 2 jump into 11 to 20, and last is 29. So let's dip down to the first group and find the next number series. So here, first group. Second group. So from 4, jump to 15, 26, and 37. Please dip down to the second group. Here, 26 and 37. So in the first group, we need to minus the 11 to 2. So first, 11 minus 2 equals 9. Okay, same pattern. 20 minus 11. 20 minus 11 equals 9. So last one is 29 minus 20. So 29 minus 20 is equals 9. As you can see, the common difference is 9. So let's add. So we need to add each number to 9. 11 plus 9 is equals 20. 20 plus 9 is equals 29. So 29 plus 9 is equals to 38. So that is our missing series number with a common difference of 9. Okay, so this is our common difference, number 9. So second, so same pattern, 15 minus 4 to get the difference equals 11. So 26 minus 15 is equals to 11. 37 minus 26 is equals to 11. So the common difference is 11. So we need to add 11 in each number. So 4 plus 11, 15 plus 11, 26 plus 11, and so on. So here, 4 plus 11 equals 15. Plus 11 is equals to 26. Plus 11 is equals to 37. Plus 11 is equals to 40. 8. So 48 is the next missing series number. So 11. So here in second group, 11 is the common difference. So here, common difference, 48. So that's all. Thank you for watching.